So let's take a look at a simple example. We want to find this output voltage V0 of t in the circuit below, given that there's no energy initially stored in the system. So first of all, let's take a closer look at this statement that no energy initially stored in the system and what that means. So remember, our capacitor energy is equal to 1/2 CV squared, and our inductor energy is equal to 1/2 Li squared. And so if we have zero energy, then we can see that means we're going to have zero voltage for our capacitor and zero current for our inductor. So essentially what this statement, no energy initially stored, is telling us is that our voltage for our capacitor at 0 is equal to 0, and our current for our inductor at 0 is equal to 0. Okay, so coming back to our circuit then, the first thing we want to do in this analysis is we want to convert our circuit to the S domain. So following those 3 steps we saw in a previous video, the first one is to convert circuit to our S domain, or transform our circuit to the S domain. And so we can do that one component at a time. So for instance, our capacitance, we have 1/3 farad in our time domain. And so if we change that to the S domain, because we have this zero initial voltage, we're not going to have a current source or voltage source, we're just going to have the impedance of 1/SC. And so plugging in the value of 1/3 for C, that becomes 3/S. Now for our 1 Henry inductor, we have a similar thing. Because we have this zero initial current, we're going to have just the impedance of SL. So plugging in a value of L equals 1, we see our impedance is just going to be S. Now for our 2 resistors, our 1 ohm and our 5 ohm, we have no change. So we have 1 ohm and 5 ohm in our time domain. So in our frequency domain, that just stays as 1 and 5. Okay, so the only thing we haven't dealt with then is our 1 volt source and this switch that is closing at t equals 0. So what does our source become is what we want to ask. So we haven't really talked about that explicitly yet. So how are we going to deal with this? So what we can see is that for t less than 0, we essentially have no voltage applied to the circuit. And then for t greater than 0, we have 1 volt. So if we were to graph that over time, so let's say we had time, and this is our voltage input, and we know it's going to be 1 after some point, what we would have is something that looks like this. So we'd have 0 for time less than 0, and then when that switch closes at 0, we're instantly jumping up to 1. And so that should look familiar because this is just our unit step function u of t. So we can say that our source is u of t in the time domain, and taking our Laplace transform, that becomes 1/S. So that's how we would handle that source. And sometimes you'll see the sources explicitly labeled. Maybe instead of having a switch, our circuit is closed, and we're explicitly told that this circuit has an input voltage of u of t volts. So you'll see both, and we'll actually see both in a later example as well. So with all of this information, we can now redraw our circuit. So we have a voltage source, and now we're not drawing the switch because we've already accounted for that when we change this to a value of u of t, which becomes 1/S. We have our inductor, and in this middle branch we have our capacitor. And so again, because we had no initial energy, we don't have to include a current source or voltage source for our capacitor or inductor to represent initial conditions. So we have 1 ohm, 5 ohm, 3/S impedance, and an S impedance. And so keep in mind what we're trying to find is this output voltage here. Now that we're in the S domain, this is capital V, and it's a function of S. So now we're on to step 2. So we're doing our analysis in the S domain. And so remember, our analysis, we can use any type of technique that we saw for our DC analysis for our standard circuits. So for this circuit, a few good options would be our node voltage method, our mesh current method. We could also do source transformations and impedance combinations. So any of these would be good options. So what we're going to do here is we're going to focus on doing the node voltage method. But if anybody has any questions or wants to see how you would do any of these other methods, please don't hesitate to let me know and I can go over that in detail as well. The reason I say node voltage method is a little bit preferable here is we can go back to our basics of node voltage. We can say we have two essential nodes. So NE equals 2, so that means we need 2 minus 1, just one equation. For our mesh current, we have two meshes, so M equals 2, number of meshes, which means we would need two equations. And with our source transformations and impedance combinations, we'd have more steps. Granted, they would be simpler steps, but it is, again, sort of more time consuming. So let's take a look at our node voltage method. And so the first step for that is we want to define our reference node. So let's say down here in the bottom, let's make this our reference node. And then this is going to be our node 1. So we can say we have voltage V1 across here. And so implicitly, that's V1 of S, or I could explicitly write that it's a function of S as well. Typically, I'm not going to keep track of that just because we don't want to get confused with having an extra S floating around. Okay. So we're then going to write an equation at node 1. So let's see if I can keep that on the screen for a little bit. So at node 1, doing the same technique we did before, we have our voltage V1 minus the voltage of the source on the left. So V1 minus 1 over S, and that's divided by the resistance of 1. So remember, for node voltage, we're essentially summing currents. So I've just done the equation for our current going out the left. Now we're going to do an equation for our current out the bottom and our current out the right. So our current out of the bottom is going to just be V1 divided by that impedance of 3 over S from our capacitor. And then our current going out the right is just going to be V1 divided by the sum of those two impedances, 5 plus S. So we can combine those two in series. That's all of our currents, so we're going to set that equal to 0. So if we're doing this analysis by hand, what we can do is collect our terms. So we can say V1 times, so we have 1 plus 5, not 5S, over 3, plus 1 over 5 plus S, and that's equal to, on the other side, I'm going to gather my constants, which is just going to be 1 over S. And so by constants, I should say it's just terms without V1, not necessarily constants. So what I can do now is this term being multiplied by V1, I can find a common denominator. So I can say this is V1, and a common denominator, the easiest way would be to just multiply the three denominators together. Of course, this is implying this is 1 over 1. So we have 3 times 5 plus S, which becomes 3S plus 15. So we have 3S plus 15. So our 1 is just going to be 3S plus 15 divided by 3S plus 15. Our second term is going to be 3S plus 15 times S in the numerator. So that's S squared plus 15S, plus 5S, divided by 3S plus 15, and here we have plus 3 divided by 5 plus, 3S plus 15. Okay, and all of that is still equal to 1 over S. So now that we have a common denominator on the left, we can combine all of these terms. And doing that, we get that this V1 is being multiplied by, so our 3S plus 15 is our common denominator. And now combining all of these, we have S squared plus 8S plus 18 is equal to 1 over S. And from there, we can pretty easily solve for our V1. And that is equal to S cubed plus 8S squared plus 18s, and in the numerator we have 3s plus 15. So here we found our V1. And so in a later video, I'll go over an easier way to do that using MATLAB or some similar software. But we can see it's a lot more complicated than if we just had a time domain circuit with one node voltage equation. But let's keep in mind that was our V1. We want to find this V out of S. So what we can do now is we can use voltage division. So let's use our voltage division to find V out. So find V out of S with voltage division. So we can say our V out of S is equal to our V1, and again we can write explicitly that that's a function of S, and then coming back up here to our circuit, let's see what we need to multiply that by. So we're interested in the voltage across S, so that's going to be in the numerator, and it's a series combination of 5 and S, so we're going to have 5 plus S in the denominator. So we have S divided by S plus 5. And so what we can see is that in our numerator we have 3 times S plus 5. So this is just pulling from this equation for V1 here. In our denominator, if I factor that S back out, we have S times S squared plus 8S plus 18. And now we're multiplying that V1 by S divided by S plus 5. And so what we can see is that our S term is going to cancel out with this one, and our S plus 5 will cancel out here. And we have our V out of S is equal to 3 divided by S squared plus 8S plus 18. Okay, so one step closer, but let's go back to our initial problem statement, and we can see we wanted to find V out of T, not V out of S. So what we're going to do now is we're going to use our inverse Laplace transforms. So what we want to do now is take our inverse Laplace transform to find our V naught of T. So now we're on step 3 of that general application. So we've done our analysis, we've solved for our value in the S domain. Now we need to inverse transform to get back to our time domain. So what we can do is we can use partial fraction expansion. So let's say using our partial fraction expansion, we can see that we have 2 poles. So we have poles at S equals -4 plus or minus j root 2. And so that comes from looking at this denominator. So what we can do is we can use the quadratic equation to find the roots of that denominator function. And we would of course have some imaginary term in that radical, which is where this j comes from. So we have some complex poles. So we could go through that process where we saw for case 3, I believe it was, for our inverse Laplace transform of distinct complex poles, and we could solve for that, but there's an easier way that we can do this. And so this is something that comes with practice, but what we could do is we could rearrange the form of this function a little bit. So if you bear with me for a second, what we could say is we could say that this V naught of S is equal to, and I could have S plus 4 squared plus the square root of 2 squared, and in the denominator, or sorry, the numerator, I'm going to put a square root of 2, and to sort of account for that, I'm going to divide by a square root of 2 over here, and I'm going to keep this 3 that we had initially here. And so if you factored this out and went through that, you'd see that this is the same as this expression up here. So you might be asking yourself, why on earth would I change it to this form? This looks a lot more complicated, and like why are we even doing this? Well, if we look at our transform pairs table, we can see that this actually corresponds to a transform pair for a sine omega t, where our omega is equal to this value here, and we have a time shift now of 4, so we can handle that with our time shift property, or rather our frequency shift property, because this is a shift in frequency, and then we just have some constant out here that's being multiplied by this function. So instead of going through that case 3 and using our residue method with these poles, if we rearrange it to this form, we can just sort of transform by inspection using known pairs. We can say then that our V out of t is equal to that constant term, which is 3 over root 2 times e to the minus 4t, so that's from our frequency shift, times sine of root 2 times t, and that's going to be in units of volts. So again, it takes some practice to be able to see how to do this. It's never wrong to go through this method of partial fraction expansion. It can just take a little bit more time. If anybody's curious how to see this particular problem worked with the partial fraction expansion, please let me know and I'll be happy to go through that as well.